Good morning. Thanks very much for the organizers for the opportunity to be here. It's my first time here. It's like a paradise for physics. And in the middle of Manhattan, right? So I didn't really know what will be interesting for the audience. I gave a very general title and a very general abstract. With the diversity in the audience, I still don't know. So instead of going too detailed into one specific thing like I usually do, I will do something different. I will give you a very quick but brief overview of some of the different things we do with the polaritons, in the hope that you may find something interesting and maybe we can discuss more afterward. So this is my slides I always use for introduction of strong coupling, which is not really necessary for this audience. Basically, strong coupling happens when the interaction between the exciton-photon becomes coherent and reversible. And we typically need to do that for a quantum Waals system. We need to do that by putting the quantum Waal in the high-quality cavity to enhance the coupling. And once we're in the strong coupling regime, to me, the interesting thing about the polaritons is because of course, this hybrid nature of matter-light hybrid particles. The matter part gives us strong nonlinearity and rich many-body physics. The light part makes it possible to study quantum features at very high temperatures and also give us a built-in interface for experimental accessibility as well as to study open dissipative physics of many-body systems. So a lot of very interesting things has been done with the polaritons, starting from good old BEC and the lasing physics to a plethora of many fascinating phenomena that logically can be described by the Gross-Pitafsky equation of a nonlinear coherent liquid. And more recently, people are looking at how to build microwave devices and Hamiltonian simulators with coupled polariton systems. To do all of this, to do them better or to do more, we will need more and more and better control of the polaritons. And fortunately, as a light-matter hybrid particle, we can control it by both its matter part and its photon part, which is often more powerful from the experimental perspective. And that's sort of motivated a lot of what we have been doing in the past few years to develop a cavity system that allow us to have versatile control of the properties of the polaritons. So I'll first introduce the type of cavity system we have been working with. As it may show you, you don't have to always use planar DBR cavities. And this may be interesting to some of you, particularly working with the polymers, organics, or some other different materials. And we'll discuss a few nonlinear phenomena we have studied using this system. And at the end, very briefly, mention how we can also build a cavity for 2D materials that also have a designability built in. So how do we control the properties of the polaritons? Conventional cavities are made planar DBRs. They are robust, they are very nice to work with, but they're also very stubborn against any modifications. So that motivated us to change it drastically by getting rid of the top DBR and replace it with a photonic crystal. And the simplest type is just a 1D grating. So I should mention that the whole thing is still epitaxially grown as far as for gallium arsenide materials. So the top layer is actually aluminum gallium arsenide, the same as one of the layers in the bottom DBR. So there's no metal loss, there's no additional loss by deposition, whatever. We basically grow the similar structure, but shorter than the conventional cavity, and then do E-beam etching, E-beam lithography and etching and selective etching to create the top grating. So if you make this sub-wavelength, there's no diffraction. And using the very high contrast of the index, one can actually make this simple 1D grating to be a very high quality mirror, even better quality than the DBRs in some sense. It has broader bandwidth. Over a very narrow range, it can almost perfect reflectance. And as a result, we can create a cavity of as high quality factor as DBR cavities with a much shorter top mirror. And the best yet, now that with the grating, we have many grating parameters or design parameters to change to control the properties of optical modes, which for polaritons directly translates to controlling the properties of the polariton modes. And that's how it is, how the actual thing looks like. That's the side view of the bottom DBR, tall bottom DBR stack. the cavity where the quantum wells are embedded and protected inside. This is sacrificial layer we will remove later, and the top is the grating. After removing the sacrificial layer, I have the grating suspended over the cavity at the bottom. And here's the top view. And we can change the size arbitrarily, obviously. So with a small size, we get a confined system almost for free. So we can check how well it works. So this is the structure. We pump outside. We see flat, broad exciton emission because there's no good mirror out there. If we pump inside, but look at the wrong polarization direction, we see the same exciton emission. But if we look at the correct polarization, we see right away the split branches, the upper and the lower polaritons, and the modes are discrete for the polaritons because we have a very small system and with strong natural confinement. And we can compare it to the theoretical models, and they match very well. The solid lines are theoretical curves, obviously. And we can also get from there the various parameters of the system. So you probably all know we can easily measure both the real space and K-space properties for the Polariton system by Fourier imaging or K-space imaging. And these are essentially the wave functions of the polaritons in K-space and in real space. And with the grating, we have a very strong polarization selectivity. As shown here, this is for the TE mode, and that's for the TM mode. They're very strongly linearly polarization selective, and that will become important for some experiments later. Now that we have such a designed system, we can play all kinds of tricks with it. We can make it into different shapes. We can put inside a small defect, and that gives us basically a cavity to produce vortex beams. And we can break the rotation symmetry of that defect. Then we can produce actually a preferred vorticity instead of vortex and anti-vortex at the same time. And we can also change it to, for example, in this case, it's a fun case that if you look at the polarization, that's a good cavity radially. So that actually gives us a vector beam that's polarized radially. So you can make a laser that produces vector beams. And of course, dispersion is a very fundamental property of any particle, quasi-particle system. It determines a lot of the important properties. And typically, we need a lattice to engineer the dispersion. But in this case, we can even engineer dispersion of just a single system. That is essentially given by the angular dependence of the reflection phase of a cavity, which is fixed for DBR to be either 0 or pi. But for the gratings, we can change it quite arbitrarily. So we can make the dispersion steeper, flat, flip it around, or even double well shape. That again gives us a lot of room to play with different things that can happen. And of course, it's also straightforward to just chain these cavities up to make different arrays. And here's just an example. If we put them apart, we get two decoupled cavities. If we put them closer, we have a coupled cavities of a common ground state. And if we chain them up into array, we get band structures. And you can also extend it to two-dimensional lattices. And you can also plant in random defects and to look at what happens with in the disorder, the system. So there are a lot of things we can play with, but we start something simple to look at what we can do. So we first go back to just a single polariton and make sure we actually can get to the nonlinear regime or create a coherent polariton system. And so starting with the discrete system, we increase the pump power, and this is something you probably have also seen many times. It starts with a non-equilibrium distribution, but eventually all the population goes to very much the ground state and corresponding to the stimulus scattering threshold. If we can take a more detailed look at the input-output that shows the stimulus scattering threshold. The line width stays narrow and it decreases across threshold. The blue shift is gradual and relatively small. There's no sudden jump. And we can look at the coherence properties of the system. So second-order coherence was one of the first things we have studied for Polariton lasers, but typically it's very hard to get it to the Poisson limit because of many reasons. But in our system, we actually made it to be sort of a perfect fit for the best second-order coherence or to reduce the intensity fluctuation. With the discrete modes, we can suppress the mode competition as well as quantum or thermal depletion of the condensate. The confinement also increases the exciton-exciton interaction and it reduces the gain saturation parameter, which makes the G2 to drop very fast above threshold, and it really goes to the Poisson limit. And we can also investigate the role of mode competition in such a Polariton laser. If we make two modes to laser at the same time, then indeed the G2 increases, and there is anti-correlation between the two modes that are lasering at the same time. So with a nice Poisson coherent, the Poisson limit of the laser, we can look at the intrinsic properties of the first-order coherence just by Michelson interferometer measurement. And here's the result that shows how the G1 decays with tau, which shows a nice exponential decay corresponding to a Lorentzian line shape at low pump powers or just below threshold, where the coherence time increases exponentially, sort of corresponding to the Charlottine line width. But at higher above threshold or larger occupation number, the line actually starts to broaden and the coherence time decreases. And at the same time, if we look more closely at the line shape, it turns from Lorentzian to Gaussian, or from exponential for G1 into a Gaussian decay in G1 tau. It turns out it actually can be very well described by a simple analytical model that was first developed for single-mode metal wave lasers, where we consider reservoir coupled to the lasing mode and include the interaction between the particles in the lasing mode. So in the low occupancy limit, where the interaction is weak, we recover the Charlottine formula. But at the high occupation limit, where the total interaction in the lasing mode becomes strong compared to the outcoupling of the dissipation, where actually this term actually dominates, and we obtain this Gaussian broadening of the line width. And that also gives us a way to be able to fit our spectrum and extract those dynamic parameters of the system, the saturation parameter, the decay, as well as the interaction strength. So this was already first described for atomic lasers, so it's not unique to polaritons. But the nice thing about polaritons is the interaction nonlinearity is stronger. So such a line broadening was actually not seen in atomic lasers because interaction is relatively weak. And it's actually quite pronounced instead in the polariton systems. But you could say that if one works hard enough, you will be able to see the same thing for atom lasers. So what could be something that's more unique to polaritons? One thing is this BCS crossover that dates back more than half a century ago, where we have an analogy of the BCS state. But for the polariton system, instead of two particles pairs into a Cooper pair, we can have particle-hole pairing plus a photon in the mix. Also, polaritons have both strong nonlinearity and basically intrinsic built-in dissipation that you can't get away with. But that also leads to some phenomena that's quite unique to such a system. So let's look at the first one, the BCS-like states of the polaritons. So these are probably two topics that will be more controversial, so I'll go a little bit more into it. So there could be some more discussions. So the BCS for the BCS state has been, of course, very well known. And shortly after it has been described the superconductors, it was realized a similar state can exist for the excitonic system for the pairing between electron hole in the high density limit when the Coulomb screening is strong. So there isn't a strongly bound state in real space, but there is still bonding in K space, just like in the BCS state. Peter, Jonathan, and Mozilla were the first ones to generalize to the polariton system to include the photon coupling. And more recently, there were also theoretical work to show that in the polariton system, one might even get such a state even without any Coulomb interaction with the coupling just produced by the photon fields. And there have also been some experimental work, but it's not very convincing in some ways. So what are those polariton BCS states? It's essentially an intermediate regime between a Polariton BEC and a photon laser. So at the low density, we have the Polariton BEC that is very well established and known already, that we need the density to be much below the Mott density so we can describe excitons.
So I was wondering, in this BCS state, do you have the notion of hole and electron Fermi surfaces? And are they the same, actually, or they're different?
That's a good question. Their mass is not exactly the same, but so far we approximate that as similar.
Because there is a very interesting state, which is large enough tuning a full differential state if the Fermi surfaces don't match. I was thinking, has it been discussed at all in this? Do you know?
I don't think it's been discussed very much theoretically, but it will be interesting to see what are the experimental implications and if we could see some signatures. So
now that there's interruptions, are you considering the regime where the cavity coupling is comparable or to or larger than the exciton binding? Or, I mean, because there was this discussion that you can actually enhance the binding.
Yes.
And then the mode transition for a polariton, if you will, could be larger. Is that?
So in this particular, in our experiment, the binding energy is about the same as the coupling strength or the Rabi splitting.
So is the number density greater than the Mott density?
That's what it should be if we go to the BCS limit. Yeah, so the Mott density should be larger. So the density should be larger than the Mott density. As a result, the electron hole distribution should not really Fermi degenerate as in the photon case, but is already above inversion density, and which also means the gain that's provided to form such a many-body state is actually fermionic in nature rather than bosonic, like in the BEC limit. And the corresponding quasi-particle in this case would be an electron hole photon with a BCS type of wave function. So, although of course the grand challenge is how can you tell such a state exists, which turns out to be quite subtle and difficult for the Polariton system, because most of the time we look at it through the emission and look at the spectral properties, which could be just identical among these different states. They all should emit coherent light with excellent first and second order coherence, and they also, the spectral features has been used to distinguish the Polariton laser and the photon laser in the sense that the photon laser should lace at the cavity frequency and often accompanied by a sudden jump of the emission frequency when one reaches the threshold. That has been the most common way for people to distinguish between photon and Polariton laser. But for the BCS state, both the BEC and the BCS state, we would expect a gradual frequency shift and emission frequency much below the cavity resonance. So really, to really distinguish them, one need to look at the matter part. That's where the nature becomes different. So it turns out our cavity becomes handy for that purpose because we have a strongly polarization selective cavity where one of the linear polarization couples strongly to form the polaritons, and the orthogonal linear polarization stays in the weak coupling regime. And at the same time, with the linear polarization, we ensure population balance between the spin up and the spin down population. So we can use the distribution functions for the TM that we can measure directly to infer what is actually happening for the reservoir for the TE modes. So that gives us simultaneous access to both this Polariton system and the matter component, or the matter reservoir of the system. This is a theoretical argument. We can also confirm it experimentally. There is no spin imbalance. So we can pump it by both the T and the TM and collect the emission also in both T and the TM. The different colors correspond to different polarization of the pump, so they overlap pretty well. There's a difference between the TE and the TM emission intensity because the collection efficiency is slightly different for the two, but we can look at the ratio of the two and that stays constant. So it confirms there's no spin imbalance in the system. Now we have this stored into the matter component, we can look at what is happening in the system. So we first just look at what typically one would measure. There is, again, this threshold, the drop of the line, and the very gradual shift of the emission frequency with no sudden jump or whatsoever. That's just to look like what we have always seen in any Polariton laser, including the ones I discussed a bit earlier. And one, we're just taking it as a very good, nice, coherent Polariton laser. And we can double confirm it's not a photon laser by comparing to a cavity with a more positive deduming or larger defacing. In this case, we see the gradual shift and the line stays narrow until it is basically all goes to the ground state above threshold. But in the photon laser case, we see the line broadens drastically at a certain point. The emission goes all the way from the exciton resonance up to the cavity resonance until when we finally reach its threshold, everything goes to the cavity frequency. So there's a drastic contrast between the two to sort of reasonably guarantee that it's not really the photon laser limit. But is this a BEC? If we look at now the TM spectrum, when we measure the reflectance, the solid line is the reflectance for the TM emission, for the TM mode, while the dashed line is the reference of the T emission. It's integrated over all angles, so you see different modes of the T emission. At very low excitation power, we sort of have the discrete exciton resonance that also coincides with the exciton emission. But as we increase power, even below threshold, the discrete exciton resonance disappears into sort of a continuum band edge absorption. And above threshold, of course, we have the continuum band edge absorption, as well as now finally a shoulder showing up here, which is actually gain in the TM. And so that shows that we're actually above the model transition density with the population inversion in the system. And it cannot be a Polariton BEC. But it's also not a photon laser, so that sort of leaves us no choice, but we actually have a BCS-like state for the Polariton. But we can put it in a bit more firmer ground theoretically, and that is we have to resort to our collaborators. And Rolf Binder at Arizona worked for years on this problem because I wasn't crazy enough to start from looking for BCS. We started with a very, very humble motivation just to want to understand better the blue shift. Because now we can measure the exciton and the polariton at the same time instead of assuming some exciton or cavity frequency. So we can measure the shift much more reliably and what is really going on with the interaction. But we just cannot understand it once we have those extra information until we look at the TM and find the exciton actually disappeared. So look at absorption, find exciton disappeared. So using the BCS model, he actually could reproduce the experimental results very well. And I'm not a theorist, but if you talk to him, he will tell you how confident he is that, or how hard it is to reproduce it. So he has a lot of confidence in his calculation. And after that, then we can use the model to look at somewhat more macroscopic picture of what's going on in the system. Here's the comparison of the different limits. This is the solid line of the Polariton BCS states. This dashed dotted line is a comparison with the ideal BCS in the thermal equilibrium limit without dissipation. The solid line considers a non-equilibrium system as well as dissipation, as well as temperature effect. So in terms of distribution, you could see that both are above the inversion, but has a lower distribution, occupation compared to the ideal BCS. Well, the photon laser has a very strong Fermi degeneracy and spectral hole burning. If we look at the polarization, which corresponds to the coherence in the system, the ideal BCS state, of course, has very high coherence over a large range of K vectors. For the Polariton BCS, because of the dissipation and everything, the coherence is much weaker compared to the ideal case, but it still spreads over a large range in wave vectors. That's more characteristic for the BCS state. And in comparison for the photon laser, it is very sharply peaked around the K vector corresponds to the cavity transition frequency. Then one can also estimate the BCS gap in the BC limit, that essentially corresponds to lower upper Polariton splitting. For the ideal BCAs, we have a very large gap, but that's significantly reduced because of, again, dissipation and the thermal effect and photon scattering. But it still remains at a reasonable range compared to the line width. So that's sort of a story of the BCAs. If you have questions, then I will move on. So dissipation here apparently has a bad role. It decreases the coherence and it reduces the gap. But in some cases, dissipation can also lead to phenomena that's interesting compared to a closed system. And this is a phase diagram produced by Euro Rubel and his colleagues with many different stable, unstable, and fixed point, etc. And one particular thing they predicted is if you take two coupled systems, you actually can get a micro-frequency cone through the limited cycle. The basic idea is that with the two coupled condensates, we all know that we can have Josephson coupling, which is a coherent coupling reversible between the two. But when we add dissipation, he proposes that you can describe that as introducing a dissipative coupling term. What that means is that in this case, the coherent coupling leads to a ground state with a lower energy and the first excited anti-bonding state with higher energy. So this would be the preferred ground state energetically. But what dissipation does is that they can make this state have a large decay rate compared to this excited state. And as a result, the system might actually prefer this state from that perspective. And this competition basically leads to a wider phenomena than just a condensation into the ground state. And that is described by this dissipative coupling term, which turns the coupling term from basically into a complex number. And here's the sort of the simplest model you can write down for this system with the psi1 and psi2, the order parameters of the two sides. We have a gain and a loss, the coupling between the two, and the nonlinearity, onset nonlinearity. Except here, now all these three terms becomes complex. And in particular, we have the coherent Josephson coupling and this dissipative coupling. The theory says that if you solve this model, it turns out it can reach a phase which corresponds to the limit cycles that give us periodic doubling to produce those multiple frequency lines from the original two states. And there are some signatures of that, which is that it needs to have a non-trivial phase relation between the two sides that's neither 0 nor pi. And although equidistant frequency lines, they should be coherent with each other. And also they would have asymmetric distributions or occupations of those different frequency lines. So how do we implement that experimentally? With our grating, we can easily make them a confined system. So we can control the string releasing at the boundary to control the bending of the grating. As a result, we can change the cavity length, which produce effectively a confinement potential for the polaritons. So we create such a double well confinement potential with the two sides with certain coupling between them. Now if we crank up the pump power, we can see the nonlinear threshold here. The black line is the total intensity. The red and the blue corresponds to intensity from each of these two sides. If we look at the ratio between the two sides, this corresponds to the, I think it's mislabeled. This two corresponds to the bonding and anti-bonding states. So if you look at the ratio between the bonding state, the single particle ground state, and the anti-bonding state, the first excited state, it responds with more population in the bonding state until at a certain point they switch to more population in the anti-bonding state. So here's the spectrum where the bonding state dominates, but we increase the power, the anti-bonding state starts to have a larger population. This is called could be sort of what they call the weak lasing regime, where the excited state gets somewhat more preferred because of the weaker dissipation. If we go even closer to the threshold, we start to see multiple frequency lines here. And you can, the line width is not much narrower than the separation, but you can still tell there are multiple frequency components inside there. So again, I was not really crazy enough to look for the frequency cone. Most of my best friends are theorists, but I secretly think most of the theories are too crazy to be realistic. But and here we saw those different lines, and we just couldn't find a way to explain it, and discovered the theory that explained it very well. So this is the range of the ground bonding and anti-bonding states. Well, that's the next excited state. So it's really far from them. Just the different frequencies just come out of nowhere unless we have those mechanisms to produce them. So if we go even higher power, we eventually should go to the ground state or the bonding state lasing. So as a summary, basically, as we increase the pump power, we start from the thermal state to sort of a first stable fixed point correspond to anti-bonding state lasing till the limited cycle regime, which is the unstable fixed point for the system that have those spontaneous oscillations. It's also expected to be a precursor for chaos for the system. And we can take a closer look at the properties of this limited cycle regime. So those different lines should be coherent with each other. So we can look at their first order coherence. And there is some beating or coherence revival. And in this one, we have clearly 4 lines. The revival is actually hardest to see, although it's reproducible and unmistakably there, because there are multiple lines. So the spectrum is messy. And because the occupation is asymmetric, that also makes the beating pretty messy and hard to see. But you can tell they're there. And we can compare it with the model that can sort of reproduce the main revival peaks in the beating. We can also look at the K-space, where we expect to have a spontaneous current that should show up in the asymmetry in the K-space or a shift of the K-space distribution. And you can see that clearly. At low pump power, it's very symmetric. But as we increase the pump power, we see a clear asymmetric shift for these low energies, while the higher energies remain, the excited states remain symmetrically distributed in K-space. And the last telltale is the phase relation between the two sides. We can magnify one side and interfere with as a reference and interfere with both to measure the phase relation. That's shown here, the two sides. They have a slight shift, which you can also plot out more clearly in the line spectrum. There is a shift in the phase, which is about half pi in this power, and it decreases toward 0 as we eventually go into the bonding state lasing limit. So basically, we think we have seen limited cycles in the pair of coupled condensates. It results from both nonlinearity and the dissipative coupling between the two sides. And that gives us those new frequency lines, beating in G1, asymmetric K-space distribution, and the interesting phase relation between the two sides. Interestingly, they also have some potentially technological implications as a new way to generate equidistant frequency lines.
What is not clear to me is what's the role of the Polariton condensates here, because you could do the same thing with coupled lasers, right?
You need a nonlinearity.
Yeah.
Lasers will work if you
Yes.
have sufficient nonlinearity.
Okay.
Yes. This is a nonlinear, peculiar for nonlinear dynamic systems.
Yeah, so people have shown this chaos and things like that with two coupled oscillators or laser with the feedback and so on, right?
If you
Yeah.
if you have nonlinearity built into it, yes.
Just, you always have a nonlinearity in a laser.
Just how strong it is.
Right, exactly.
Yeah.
Because, I mean, four-wave mixing will by nature be there and
Yes.
will lock modes together.
So I still have a little bit, I'll go very quickly just in case some,
2 minutes.
okay, some of you may find this interesting.
I mean, you know, it takes from the discussion time, so basically up to you.
Okay. So again, 2D materials don't need a really introduction. What we make use of in this particular case is the very large binding energy and the strong exciton-photon interaction, and of course the fabrication flexibility. So with gallium arsenide and the traditional materials, we need lattice-matched heterostructures. That's why we need to keep the quantum well inside of the cavity and use the photonic crystal as a reflector instead. But with the 2D materials, we can use the photonic crystal itself as the resonator. Even just to take a 1D grating, again, we can use the guided wave resonance mode of this grating as our cavity mode, and put the 2D material simply on top of it. The field is evanescent outside of the grating, but within 1 nanometer, it's still very strong. So it couples very strongly to the 2D material. And of course, we have even greater designability with a real photonic crystal mode. So here's just an example that you can simply change the period of the grating to have the resonance couple all 4 commonly studied transition metal dicotyl-nides. And that's the experimental results, which is strong coupling is almost inescapable in this system. You have the grating, you put the 2D material on top, and you get a strongly coupled mode or the anti-crossing. And with a bit better line width, you can get the anti-crossing at room temperature as well. And with those grating modes, you also have this funny funnel line shape that, again, gives certain tunability, depends on what you want to do. And better yet, with such a strong exciton-photon interaction, you can get to this coherent exciton-photon interaction limit even without a cavity. So it's been shown that if your exciton-photon coupling strength becomes much larger or large compared to any dissipative mechanisms, the absorption actually will be reversibly coherently emitted back, which results in very high reflectivity of the system. And that means now we can control the radiative decay to see the effect when we change the radiative decay very clearly and directly. So we put a mirror under the 2D, behind the 2D material. As we move the mirror, we change the vacuum field distribution, and that will change the radiative coupling of the system. And what can happen? Actually, a lot of interesting, very basic quantum optical phenomena, but very hard to see in other systems, becomes very pronounced and easily observable in this system. As we move it, for example, the line width oscillates as one expects because we modulate radiative coupling, and correspondingly, the collective line shift shows up with a phase shift compared to the line width modulation, which hasn't been seen in semiconductors just because inhomogeneity and everything else dominates in other semiconductor systems. And very interestingly, when you modulate it in the very coherent limit, you have high reflectance, right? You can go to the limit where reflectance is low. And in between, you actually reach so-called critical coupling where the radiative decay balances the incoherent scattering. And at that point, we actually can get almost a perfect absorption in this system. It's actually 4%, so we get a 99.6% absorption in just a single molecular layer, which is, the math works out simple, but I found it quite remarkable. Okay, that's all, and those are the people who actually did the work, and our collaborators and sponsors made it possible. Thank you.
Questions, comments, discussions?
So I actually have 2 questions. So in this BCS laser, so what evidence is there that makes it BCS, essentially? Why do you call it BCS?
So it's a good question. How do you prove it's a BCS? We are sort of in the way of doing exclusion. We have an inversion and a fermionic gain that shows it is not really a BEC Polariton laser. And it's also clearly not a photon laser with the electron hole plasma. The frequency is much below the cavity frequency. You could say theoretically that shows you still have a bound state in the system that gives this frequency shift. And ideally, you would want to measure the gap, but one could argue you can also see a photon hole burning gap, even in a conventional laser.
So my second question was actually kind of the same question asked during the talk. In this particular case, though, in your actual experiment, how different are the effective Fermi surfaces from holes and electrons in numbers? Well, you have, I mean, to have BCS, you must have Fermi surface, otherwise it doesn't make, there's no BCS without Fermi surfaces.
Oh, I'm sorry, may I just clarify, your question is the number imbalance between electrons and holes?
Yes, I mean, you have, you pair electrons and holes.
Yeah, I understand, but
So,
the question is the number imbalance.
I mean, number of balance, whatever you want to call it, but
There's also shape.
I know that, but that's why I was asking, which of the two was the important one?
I mean, I would say that for BCS, you want identical Fermi surfaces. If they're not identical, it's actually not BCS. So, do you know anything about the effective Fermi surface?
Unfortunately, I don't know the numbers. As the theory didn't neglect the difference in the effective mass for electron holes in this way, in this case. So, but the number should be the same, but there'll be an imbalance in the K distribution.
Okay, so I think we have Peter, Jérôme.
Good. Well, no, so thank you for this. And of course, we've talked about this a lot. So, but let me sort of, I think, restate Victor's question a little bit. Obviously, the crossovers actually in these phase diagrams are complicated because there's no change in the broken symmetry, as you point out. So, the one clear thing that one might hope to see would be a spectroscopic gap, right? And as I understand it, in terms of the fitting of the theory, there's a lifetime which is introduced, which is considerably larger than that gap, only by about a factor of 2. But that means that you're in a limit that it's a gapless superconductor. So that's.
So.
I mean, so yeah. So I mean, so but there's also another hidden thing behind this, which is that we're really thinking that the transition is going as a function of density because, if you like, collisions, interactions between the excitonic component are the force that breaks them up. Now again, I can destroy excitons by incoherent processes which are different from the ones which are associated with their interactions. So that does produce a question. Sorry about this. And the question is, what's the density, and do you have an independent measurement of what the exciton component of the density is at the point where you see a transition?
So the density is about the Mott density. We can measure it reasonably well because we do have these weakly coupled excitons. I'm not sure I have the numbers there. So we do measure just the, we can compare the emission intensity, calibrated emission intensity into how many carriers in the system. And we can compare that with the pump density, what we put in the system and convert to a number of carriers. And these two matches within a factor of 2 in our calibration. So we're reasonably confident with our density. And this is the horizontal axis is the experimental.
So right, so you're confident that this is within about a factor of 2?
It's around the Mott density, yes.
John?
Very short question. Thank you, of course, for this very nice presentation. Those are gallium arsenide wells?
Yes.
Wouldn't you expect a rather different, I mean, this process to be quite different if you had strained in gas, because there this asymmetry between electron and hole should be much smaller, because your density of state, the hole would be actually much smaller. So in a sense, this asymmetry that sort of arises as you raise the temperature, because it's known that in a laser, if you're close to room temperature, your valence band is non-inverted. All inversion is in the conduction band. And this asymmetry, of course, is not something you would see in a BC. So you probably could perhaps see a very different behavior if you were now working with a strain in gas.
With strain versus, that's interesting. Yes, the strain will be much stronger in gas, although all the experiments are done at below 10 Kelvin.
Yeah, sure, of course. No. Okay, go.
I think Atash had a question.
Yeah, so it's actually maybe also a question to Peter and Jonathan. I mean, could one use a terahertz field to detect the presence of a gap?
Yes, that's an excellent question. I think that is definitely something one could try. Yes.
And the other point is, I don't know how much it will have, but it could address the question that Victor raised, that if you if you have access to high magnetic fields, it was discussed that if you can really keep your cyclotron frequency above other energy scales, basically the original bands do not matter, and then you should have symmetric conduction and balance. But I guess it's more than 10 Tesla.
Yeah, yeah. Maybe we can see if we can do the experiment at Rice.
Okay, well, let's thank you again.